Everybody, my name is Vladan Jevremovic, and today I will be talking about tips for designing in-building industrial IoT networks. I'm going to focus on use case of sensors in a factory. Their value is that they are flexible, they can be placed anywhere, and the cost is favorable because there is no cabling. And the technical requirements that we will be focusing on is that they are high density. There is about one sensor for each square foot. Reliability needs to be high, 99.9999%. Coverage must be 3D because there are high ceiling in the factory. Power consumption must be low because they're battery operated, battery powered. And data rate is low volume. It's 20 kilobits per second, but the nature of transmission is bursty. They may transmit every once in a while, but most of the time they're quiet. So what does 99.9999% reliability means? Well, first of all, radio frequency signal has Gaussian distribution. Okay, it is statistical in nature. In a fixed location, the signal can vary in time, and the variations are characterized by mean value and standard deviation at that location. When we take a look at this graph, we see that everything is centered around the mean value. That means that 50% of the time when I measure a signal in particular location, it is going to be greater than mean value, and 50% of the time it will be less than the mean value. But things get a bit more interesting when we take standard deviation into play. If I subtract one standard deviation from the mean value, then I'm going to calculate that value, and when I start measuring, if I have enough measurements, I will see that 68% of the measurements will be greater than that value that I calculated, which is mean minus one standard deviation. So we formalize this observation in this table. This table will tell you what happens when you keep subtracting 1, 2, 3, 4, and 5 sigma from the mean value. And you will notice that the very last entry has 99.99994%. So what does it mean? When I calculate mean minus 5 sigma, then most of the time, which is, if I take million measurements, 999,999 out of million, I'm going to measure a signal that is greater than mean minus 5 sigma, and only 1 in million, it's going to happen that the measured value is less than that value. So that really means that to achieve that reliability, I have to have the minimum mean signal to be 5 sigma greater than sensitivity, because sensitivity is the lowest detectable signal in an RF channel. But how do we calculate sensitivity? Well, if you take into account a 5G MR channel that has a resource block that has a 30 kilohertz wide channel, and if you assume that the receiver has noise figure of 8 dB, and if you assume that the standard deviation, indoor standard deviation is 5 to 6 dB range, then the calculation is as follows. First, you calculate sensitivity, which is minus 174 plus 10 logarithm of the bandwidth of the channel plus noise figure. And that calculates to be minus 121 dBm. So areas on the floor plan where RSRP are greater than minus 121 dBm are in coverage. The areas where it is less than that, they are in outage. So the minimum RSRP signal to achieve that reliability that we talked about, 99.9999%, is sensitivity plus 5 sigma. And if we assume that standard deviation is 5 dB, then it is minus 121 plus 5 times 5, and that is minus 96 dBm. So if the coverage is minus 96 dBm or higher, then we are in good shape. We guarantee the desired reliability. At the very edge of the coverage, in the areas where it is minus 96 dBm, 1 out of 1 million measurements will be less than that, and that means that we will have the signal that is not going to be detectable. So that is how we translate the desired reliability into coverage. Let's now take a look at the capacity. We said that we want to take a look at car factory. I have a car factory that I will use in a demo that has 1.17 million square feet. That means that we are going to have 1.17 million sensors because, as I said, it is one sensor per square foot. If they're transmitting in 20 kilobits per second bursts, and if they transmit 1 second at a time, and if they transmit twice per minute, that on average I will have 39,000 sensors active at the same time. That is on average. I'm going to assume that they are equally distributed on the floor plan, and then I also have to assume a certain target average cell load. And it has to be less than 100%. I am going to this exercise require that the cell load to be in a 70 to 90% range. So why less than 100%? Well, I said that on average 39,000 sensors can be active at the same time. This is on average. At any given point in time, it can be less than that or more than that. Without getting into details, you must keep in mind that you have to have less than 100% so that you account for that activity when you will have more than 39,000 sensors active. So that is why you're giving a cushion there. So that is how I would approach design for capacity and for coverage. And now I'm going to show you in a demo how it looks like. So let's take a look at the demo. This is a car factory, and I said it is 1.17 million square feet. And as we said, the target RSRP should be neg 96 dBm or higher. I assume that the sensors are equally distributed in the factory, so that means that I would want to have 100% of the coverage that is greater than neg 96 dBm. I already placed small cells throughout. This is a 3.5 gigahertz indoor network, and let's take a look what my heat map looks like for RSRP. First of all, we see that we do not have 100% of coverage that is neg 96 or higher. There are some pockets of what we see as a black area, which is the area of outage. It is very difficult to design for 100% coverage. In practical terms, what you would want to do is to identify the areas where the sensors will be and focus on those areas to have neg 96 dBm or higher there. Here I assume the uniform distribution and I targeted 100%. It is really not realistic unless sensors are really everywhere in the factory, which they probably aren't. So this shows my coverage heat map. Now let's take a look at the capacity. First of all, we have to define in our tool, we have to define how many sensors we should have in this factory. I did say 1.17 million sensors, but because of the activity, as I argued in the previous slide, we only have 39,000 on average that are active at the same time. And that is on average. It could be more, it could be less, but we are designing for average right now. The usage profile is car factory sensor. So what does it really mean? If we click on that, car factory sensor has a 20 kilobits per second transmission. That is a burst. So all those 39,000 are transmitting at 20 kilobits per second at any given point in time. So having said that, then we run the capacity heat map, and what we are going to get after we complete is the map that will have either green, which means it passed, red, it failed due to the air interface, or dark red, it failed because there are too many connections that are requested. So what do we see here? The cell load that we calculated, assuming 39,000 sensors and assuming they're 20 kilobits per second each, gives a cell load of 78%. I did say that I want to have between 70 and 90%. You will see that here I have a figure of cell load of 90%. It is mentioned here. And that means that I would want to go to be below that. And because 78% is less than 90%, that means that I have passed and that the whole of the factory is green, meaning that the number of small cells that I have placed in this floor plan is sufficient to support, on average, 39,000 sensors that are transmitting at in 20 kilobits per second bursts. So this was a short example, a short demo as to how you would practically design for capacity and coverage for an industrial IoT environment. Thank you.